Let us do a half space problem. So this half space is indented with a flat rigid punch. So on the rigid punch you have applied a force, let's say P of 2a times P naught, where P naught is a constant, and this is distributed over the width of the punch, which is equal to 2a, goes from minus a to a. The width in the out of plane direction for plane strain problems, we generally take it to be 1. So the area of the punch is 2a. The total load is 2a times P naught into 1. That is the total load that you've applied, and that is distributed as this. Before solving this problem, let us solve a more general problem where you have, so this pressure is applied from minus a to a, whereas in the general problem we have applied a pressure, some pressure distribution, not a constant one that varies with x2 from minus infinity to infinity. So for this problem, the normal to this direction, the normal is minus 1, 0, 0. The traction is equal to px2 E1. Remember, E1 is this is the positive E1, so traction is, and so from Ti equal to sigma ij nj, you will infer that sigma 11 is equal to minus P and sigma 12 is equal to 0 on x2 equal to 0. And as we'll see, this is enough for us to get a solution to this problem. Now, remember the solution to the biharmonic equation for a half plane problem like this was this. This was the solution to phi bar, the potential function that satisfies the Airy stress function that satisfies the biharmonic equation. Now, this is my half plane and this is my x1, and here is my loading, pressure loading, and I know that as I expect that as I go towards x1 tending to infinity, my stresses should all die down to 0. And that cannot happen if this term is there in place, because this term goes towards infinity as x1 tends to infinity, and that obviously implies that this has to be equal to 0 for these kinds of problems. So I'm left with only this part as my phi bar for half plane problems where the stresses decay down to 0. You might say these are phi bar, not the stresses, but if I look at the expressions for the stresses, they also contain phi bar. So they would also contain e to the power positive zeta x1 terms. So those, for the stresses to go to 0, those terms have to be equal to 0. Therefore, I can in general assume that this is equal to 0. And once I have got this, I'll get phi from here. More than that, once I have got this, what I'm going to do is on x1 equal to 0, I have sigma 11 bar equal to minus zeta square phi bar equal to minus p bar, and sigma 12 bar equal to minus I zeta d phi bar dx1 equal to 0. So these two expressions will give me, so I'll put this phi bar into these two expressions. These two expressions will give me two equations from which I can determine A and B, and then I'll get phi bar completely. That is what I have done here. So that is what I have done here. This expression comes from sigma 11 bar equal to minus p bar, and this expression comes from sigma 12 bar equal to 0. From these two expressions, I determine A and B and plug it in here. This is my final phi bar, which means now that the stresses can be immediately obtained from these expressions. These are the expressions for the stresses in terms of phi bar. So I plug the phi bar in, invert this, plug the phi bar in, invert this, plug the phi bar in, invert this, get the stresses. Displacements in the same way. So I have the phi bar here, so I'll get u2 from this expression. I have, this is an integral, remember, this is 1 by 2 pi times minus infinity to infinity, that kind of an integral. And then For u1, I will use this expression. Again, this is an integral. Whether I can evaluate the integral or not depends on the kind of integral it is, but as an integral, I can get the answers right away. So these are the answers that I get for this more general problem, where um, the, the stresses are going to be this, and the displacements are these. So I get that right away. Now, I can do some simplifications for cases where p is either an even or odd function. If p is an even function, then p bar is also an even function. P is an odd function, p bar is also an odd function. And in those cases where p is, let's say, even, in the even case, I can reduce this integral of minus infinity to infinity to an integral 2 times an integral from 0 to infinity, because p is even. And this is actually cos zeta x2 plus I zeta x2. This part is odd, this part is even. So when you do an integral from minus infinity to infinity, this part times this even function is not going to survive. It's going to go to 0, and this part is only going to remain. So this integral can be replaced by 0 to pi px2 cos zeta x2 dx2. So we will give this a name. We'll call this the cosine transform. This is the cosine transform of p bar. Okay, and this cosine transform will be denoted by a hat rather than the bar. So just note that the cosine transform is 2 times. There's a 2 time. We are defining only this part as the cosine transform. Okay, only this part as the cosine transform. And if you do that, then these integrals from 0 to infinity can be shown to reduce to integrals from 0 to infinity. Sorry, these integrals from minus infinity to infinity will reduce to integrals from 0 to infinity, all of them, and you would get very easily these expressions, these integrals for the stresses, and these integrals for the displacements. Now let us come back to our special case where we have a constant distributed load from minus a to a rather than a load from minus infinity to infinity. All we have to do in these expressions is to find, this is of course an even function. So what we have is a even function, though a degenerate kind of even function, but it's an even function nevertheless. So we can use directly. We will get the answers if we use these expressions, but it's overkill. We don't need to use these expressions. So we will use the cos expressions. So if we want to get the stresses now, all that we need to do is need to get p bar. The rest of it doesn't depend on what kind of p you apply. And to get the p bar, we have to do the integral px2 cos zeta x2 dx2. px2 in this case is a constant. It's equal to p naught. And this is an integral not from 0 to infinity, but from 0 to a, because it's 0. Px2 is equal to 0 after a. Okay, so to do that is easy. If we can get the p hat easily, and that comes out to be p naught sine zeta a by zeta. So that's what we have. Now we simply plug it in. We simply plug p hat in and try to evaluate these integrals, and it turns out these integrals are evaluable in this case. So here are the integrals after you put in the p naught. Okay, and there's okay. Now these integrals may look sort of formidable. These are the integrals that you have to evaluate with p hat given by p naught sine zeta a by zeta. So these integrals actually have been evaluated, and I'm not going to derive them. The derivations are a bit long. But they have been evaluated in a sort of non-intuitive way by Snedden. You can look at the book. The derivation is given there, and this is evaluated at any point p. These expressions, these are functions of x1 and x2. So at any point p denoted by x1 and x2, these expressions give you the stresses, right? And Snedden evaluated them in terms of three angles and distances. So the first angle is theta, which this point x1, x2 makes with the x1 axis. And r is the radial distance from the origin to this point. Similarly, r1 is the distance from the edge, left edge, right edge of the load. Theta 1 is the angle that it makes with the x1 axis. Theta 2 is the angle from the left edge of the load, and r2 is the distance that it has from the left edge of the load. And therefore, x1, so this is x1 plus I x2 plus a, whereas this is x1 plus I x2 minus a. So the complex representations of this point with respect to this and with respect to this are this and this respectively. Doing that, Snedden could express the solution of these integrals, solution of these three integrals in terms of these angles. So sigma 11, sigma 22 and sigma 12 are given in terms of the angles theta 1, theta 2 and theta in this particular manner. So this is the expression for sigma 1, sigma 11, sigma 22, sigma 12 in terms of theta 1 and theta 2. Now, again, how he got these solutions is a bit tedious. It's straightforward but tedious. We are not going into that right now, but I just want to make sure that you understand how this. So this is the punch that is exerting this force, and from the edges of the punch he defined two angles theta 1 and theta 2, and in terms of these two angles and the distances from these 2 points of any point p in the domain, these are the expressions for the stresses. Now, if you look at these carefully, you can calculate the maximum shear stress at any point. So at any point, the maximum shear stress would be given by this expression. This just appears from your stress transformations. This is also something you have done for Mohr circle, the maximum shear stress. And that maximum shear stress, if you use these expressions, that maximum shear stress comes out to be P naught by pi into sine theta 1 minus theta 2. So over a curve on which sine theta 1 minus theta 2 is constant, tau is a constant. So this curve on which sine theta 1 minus theta 2 is constant is representative of a family of circles that passes through the edges of the load. So it is representative of this kind of family of circles that pass through the edges of the load. So these circles are sine theta 1 minus theta 2 equal to constant. You can easily verify this, that circles that pass through these two edges are given by this expression. Now, if you remember in your photoelasticity experiments, the fringes in the photoelasticity experiments with quarter wave plates, circular polariscope that you have learned, the fringes, the dark fringes, are representative of points of maximum loci of maximum principal stress. So the maximum principal stress is constant over these circles. So the fringes that you see in photoelasticity are going to take the shape of these circles in um, in an actual experiment. So they are going to take the shapes of these circles. So now what I have done here is for the half plane, I have now plotted, not through photoelasticity, but in MATLAB, I have plotted these stresses. Sigma 11, sigma 12, sigma 11, sigma 22, and the tau. So they are here. So this is your sigma 11. And look at this point. At this point, the stresses are singular. So the stresses go to infinity at the edges. They are uh, they are finite. In other points, this is sigma 11, this is sigma 22, which I have plotted from these expressions. And then I have plotted tau, which we have already derived. It's singular at this edge, but it is a set of circles, set of constant taus are sets of circles that pass through the edges of the load. I have plotted only half of the domain. The other half is a mirror image. So these circles pass through the edges of the load. And these are exactly the photoelasticity images that you're going to see in a real photoelastic experiment. Okay, we can take this further and ask the question as to what happens when A tends to 0. So when A tends to 0, by the way, you will get a singular point here, and obviously on the other side, which is the mirror image, and I have not drawn, you would get another singular point. So there are two singular points at the two edges of the load. Now we ask the question of what happens when A tends to 0. What happens when A tends to 0? When A tends to 0, uh, we can evaluate p hat easily. P hat we know that is equal to sine zeta by A, and P naught times 2A is the total load that you have applied. So P naught is equal to the total load divided by the width of the punch. Okay, so I plug in P naught here, and then I take the limit A tends to 0. Sine zeta A by zeta, limit A tends to 0, sine zeta A by zeta A is equal to sine zeta A by A is equal to zeta. So given this limit, this is what you get when you take A tends to 0. And then for that case, this load, this distributed load, actually becomes a point load at the origin. A tends to 0, which is equal to P naught equal to P by 2A. So this becomes a load equal to P equal to 2A P naught applied at the origin. So this distributed load problem reduces to this point load problem when A tends to 0. And then to find the stresses, all you have to do is in this replace P hat by the new expression. P hat is equal to P by 2 that we have found for the case A tends to 0. And if you do that, these are the integrals that you get. These are the integrals for the stresses that you get, and these integrals can be evaluated. The evaluation is again straightforward but tedious, and these are the stresses that you get at any point x1, x2 for a problem where a point load is applied at the origin of a half space. Now this problem you have solved earlier using the Airy stress function method, and if you remember, this is called the Flamand problem. And we have now solved the Flamand's problem using the Fourier transform method, where we found the phi bar directly by using Fourier transforms. And you should check that the answers to the Flamand problem are the same obtained from both the methods. Displacements can also be found. I'm not finding the displacements, but now in the Flamand problem, if we define r theta coordinates like this, so r for any point x1, x2, this is r and theta is the angle measured from the x1 axis, then sigma 11, this sigma 11 here, this sigma 11 and sigma 22 and sigma 12 can be represented in terms of r and theta as this and this. Again, you see that as r tends to 0, the stresses, all the stresses blow up, all the stresses are singular at this point, and by simple stress transformation I can find the stresses in the RR direction, which is, so if I take a pillbox here, this is sigma RR, and I can transform the stresses sigma 11 to 12 stresses to sigma RR using the simple stress transformation equation, and this is what I will get. Okay, again you see that the stress is singular at r equal to 0. All the stresses are singular at r equal to 0. So this is the solution to the Fleming's problem. Why do we solve this problem? We solve this problem because this forms a benchmark solution from which more difficult solutions of more realistic problems can be derived. So for example, if you now have, so you now have this solution for p equal to 1, for a unit load applied at the origin, these solutions are called the Green's function for the stresses. So these are called Green's function for the stresses, and these Green's functions are functions that that can generate other solutions to the stress problem. For example, if I now have a distributed load problem, so I have a half space on which I have an arbitrarily distributed pressure applied, and I can use now the principle of superposition to find the stresses at this point. What is the stress at this point? The stress at this point is, for example, the stress due to a point load applied here. How big is the point load? This point load is PS, which is the value of P at this location S, times the area on which it is applied. So that is ds times 1. So PS ds is the point load that is applied at a distance S from the current origin. So now let us shift the origin here. Let us shift the origin here, and then if I forget about every other load, the stress contribution to this load PS, the stress contribution of this load PSDS is same as that of the Fleming problem with a load P applied here. So instead of the load P applied here, I now have a load PSDS applied here. So the stress contribution of this black bar would be, say, sigma 11 contribution of this black bar would be simply minus 2 x1 cube by x1 square plus x2 square whole square, and in place of P I will add PS ds. So this is the contribution, but remember that I have now moved x2 by s, so instead of x2 here, I should write x2 minus s whole square, and then the whole thing whole square. So this would be the contribution of that small black bar of load, and have directly obtained that from the Fleming solution. Now I will scan through all such DSs. So I'll go from DS starting from, let's say, A1 to B1, and all those added together will give me, by principle of superposition, will give me the total load at this point. So I will scan from my B to A. So this is B to A. I'll scan from B to A, and when I scan from here to here, I take all these small strips ds which have a contribution each of which have a contribution of this sort, the integrand here, each of these have a contribution of this sort, and then I sum them up by doing this integral, and that gives me the total stress at this point due to this complete distribution of load. It gives me the total stress sigma 1 1 at this point. If I want to do it for sigma 2 2, I exactly have to do the same thing. I have to take the Green's function solution first, then assume that the load is PSDS. So multiply the Green's function by PSDS to get the stress contribution due to this strip. Integrate from B to A, and that will give you the total contribution from all such strips that make up this distribution of loads. So this is what you will get immediately by using the Flamand solution or the Green's function solution for the half space problem. We had done a Green's function solution for a full space problem also. We called it the Kelvin problem. So in a Kelvin problem we had solved some time back. Yeah, so these were the solutions to the Kelvin problem. Stress at any point due to a force F1 applied at the origin. This can also be a Green solution. This can also be a Green's function. This is a Green's function for a full space problem, whereas this is the Green's function for an half space problem for stresses. Similarly, we had earlier for the Kelvin problem, we had found the Green's function for displacements as well. And those Green's functions can also be superposed in order to find the displacements at any point, the total displacement at any point. So Green's function solutions can be generated by Fourier transform methods, and then they can be used along with the principle of superposition to give you the solution to any problem. We will see an example of how to apply Green's function on a rather advanced problem, but a very important problem called the SLB problem of an inclusion, that we will do in the next class.